Okay, welcome back. So we talked about some past works about and the different the researchers of very important contributions by different researchers of very high stature who had different kind of views on blow off. So there is not a uniform or a consensus view on flame blow off, and but anyways we can compile in this paper, in this review paper. These authors Schanboge, Hussein and Lewin, they compiled the data from different sources, as you see this Dizue, Plumella, Zukowski, Williams, Hotel, Yamaguchi, and all their measurements have been just compiled, and they tried to find a fitting correlation between Reynolds number and Damkolon number. Okay, so Reynolds number is essentially, as you have seen, that is essentially the ratio of the inertia forces to the viscous forces, but this is a normal the diameter based Reynolds number. This is not to be confused with the turbulent Reynolds number, and this is also the Damkolon number. Okay, so you see that when you have when you compile all the data, it appears, though it's like a lot of scattered in a log-log plot, it appears that they follow kind of this Reynolds number is equal to A times log of Reynolds number plus B, that they have a scaling, has a kind of a power law scaling of between Reynolds number and Damkolon number. So this is the data that they that has been compiled. Okay. So recent works, I mean in the sense that from about 10 years ago by in the appearing this paper appearing Journal Propulsion and Power at Georgia from Georgia Tech, they observed they use this Mie scattering images only, that is they put olive oils in the olive oil droplets in the flow, and they shine laser and allow this olive oil droplets to scatter the lights, and the boundary where this olive oil evaporates can be considered as a flame boundary, and it's a roughly it can be considered as a flame boundary, and they found using that technique they found out what was the how does the flame structure look or the flame boundaries look when the blow off is approached. Okay, so they found that as blow off is approached there is an initiation of the flame hole, and it is convecting downstream. Okay, or it can heal also in some cases. Okay, and that is the flame hole can close, and however it was they also said that this flame hole, that is this that is a formation of an unbound reactant or a formation of a region of this bond product, essentially it's a formation of an unbound reactant which is called a flame hole, which is surrounded by the flame boundary or the flame front, can also persist, and the flame hole they say it was created because it is at those points there was the local extinction strain rate at those points or the local stretch rates at those points exceeded the corresponding extinction strain rates. Okay, and extinction strain rate is a property that is measured from an opposed premix flame, and it can be considered roughly as a property of a premix flame. Like it's not as rigorous as a property as the laminar flame speed, but still it can be considered as a measure for ignition for extinction. Okay, so in this reaction also in this simulation also they found that this formation of this gaps in the flames or this flame holes, that is these parts contain this unbound reactants, and here these are the flame holes that are being formed. Okay, and this was the stage 1 where this is essentially characterized by initiation of a flame hole. Okay, now the stage 2 is that just before blow off that but you see even the flame hole is created, the flame is still symmetric in shape. Okay, it does not has a very large change in it does not have a change in large scale structures, but they said that what they said is that as blow off is approached and right moments before blow off, then the flame essentially loses its symmetry and it takes a more sinus shape, which is overall the large scale structure of the flame gets distorted. Okay, and they said that this is because now the flame blow off is approached, there is a lot of extinction, and maybe that is causing the flame the flow to undergo a transition from this convective instability to absolute instability, that is from the symmetric vortex shedding as we have seen to the asymmetric vortex shedding. But of course we do not know why this is happening. Okay, and we do not know the exact mechanism also by which the flames the extinction along the flame structure is happening. Okay, So, and also these are not exact, this cannot be considered as exact flame shape or the flame contours, because these are only the boundaries where the olive oils are being evaporated. So, if there is a product region, high temperature product region, but no flame, then also we will see that the olive oil is evaporating and creating a boundary like this. So, it is not exactly representative of flame. So, we need to have better diagnostic techniques, like we need to do some laser induced fluorescence. So, with which we can better quantify or better pinpoint that this is the point where my flame is, this is the point where there is no flame. Okay. So, this is why we did this combined particle image velocimetry and laser induced fluorescence to understand the flame blow off mechanism. So, this is done in a very small laboratory scale experiment, where we essentially have this conical nozzle. Okay. And at the end of the conical nozzle you have this bluff body. You see, this is a cylindrical bluff body which is placed, which is in this shape, and we have this kind of honeycombs, etc. And this is essentially the bluff body looks like this. Okay. So, of course, it is a fundamental work, but still this kind of fundamental works can be very important towards resolving the basic physics that is involved. Okay. And then of course, you send premixed fuel air mixture into this nozzle after the fuel and air are mixed into a mixing chamber, and then you basically pass your laser sheet through the mid plane of this bluff body, and you ensure. So this Nd:EG laser essentially pumps this dye laser, which passes, and the output of that passes to this doubling crystal to produce this 283 nanometer wavelength, and by reflecting it through mirrors and creating a sheet optics like this, one basically gets this laser sheet. Okay, which forms this PLIF laser sheet. Now, this PLIF laser sheet is located exactly in the same location as that of the PIV laser sheet, because we want to visualize the PIV and the PLIF, or we want to visualize the flow field and the OH field simultaneously. Okay. And so these two are located in the same locations. Okay. And temporally this laser sheet, these lasers typically last for about 10 nanoseconds, and this runs at a frequency of about 10 hertz. Okay. So, we have to ensure that the PLIF laser sheet temporally is located exactly midway between this PIV laser sheets, these two PIV laser sheets, which are say at a difference of like 20 microseconds. So, if this is the one PIV laser sheet and this is one PIV laser sheet, so and the difference between them is about say 20 microseconds. Okay. So, the PLIF laser sheet is located here exactly midway between these two. So, this is in time. Okay. And each of the width of these things is about 10 nanoseconds. Okay. So, this is the thing how it looks like. And so, what does happen before blow off? Now, before we do the PIV PLIF, it is we can do this chemiluminescence imaging also. Now, chemiluminescence is essentially this visual this visible light emission that we see from the flame. Now, one thing you have to know that this chemiluminescence emerges from radicals which are chemically activated, and as a result of that you cannot these are not in thermal equilibrium, and from this chemiluminescence you cannot really measure the radical concentration because there is no equilibrium among them, these are chemically activated. So, you really cannot obtain the steady, or you cannot really obtain the ground state population of the radicals which are emitting this light. Okay. So, you cannot do that, but you can do that in the PLIF. Okay. So, from chemiluminescence what you can get is essentially a qualitative idea of heat release, because people have shown that researchers have shown that if you that the chemiluminescence signal is essentially proportional to the heat release rate for premix flames. Okay. So, this qualitative tells us how the heat release is. Another problem of chemiluminescence is that it is line of sight integrated. Okay. So, PLIF you can get it in one plane, PIV you can get in one plane, whereas chemiluminescence is line of sight integrated, but still you can get a qualitatively nice idea. So, what you see is that what you have near blow off, that if you this is at about taken at about 500 hertz. This work was done in late 2009, early 2010. So and mid 2009 2010 ish, and or from 2008 to 2010 something like that. So you see that here this flame which is about 6.8 seconds before blow off, it was stable here, but then it loses then you see that this sort of flame holes forming, large flame holes forming, that is there is no chemiluminescence, there is no heat release, and then you see that the flame becomes essentially sinus in structure. You see this is a sinus mode kind of developing here, and then it again re-establishes. Okay. So this thing can happen just a little bit before blow off. By the way, the here the flow is going from left to from bottom to up in each of these images, and this is the flame holder is something like this. Okay. So this is the flame holder is stabilized here, and the flame is stabilized, a T-shaped flame holder or in a cylindrical T essentially, and the flame is stabilized just downstream of that. Okay. So here you see that just before blow off you can have this kind of a sequence where you see that large flame holes are forming, and then the flame goes into this recirculation zone, and then it goes into blow off again. Now one thing to note is that in that regard that that this that if you just go back to this previous structure of the recirculation zone, say in this one. Okay. So what happens here in a recirculation zone, I mean irrespective of the bluff body, so the flame is stabilized. So this is the you have a flame here, right. So the flame is essentially stabilized. Let me use a different color. Let's use blue for premix flames. So the flame is essentially stabilized like this. Okay. So this is fresh mixture which is entraining into this flame. Okay. And as soon as it enters into the flame, it recirculates of course, but it becomes bound products. Alright. So outside you have fresh mixtures, inside you have bound products. So as soon as it enters into the flame, in this recirculation zone, what is recirculating? Okay, what is recirculating like this, and what is recirculating like this is burnt products. Okay. So for a stable flame which is where there is no extinction along this along the flames along these shear layers, as you see the shear layers are formed here, which is characterized by large values of W's omega z. So the flame is stabilized along shear layers, and inside the recirculation zone you only get burnt products. Okay, because the flame is continuous, anything that goes through the recirculation zone must be burnt products. But in such cases you see that, for example, now you see this recirculation zone contains some reactions. Okay. So the recirculation zone can contain only reactions, can contain intermediates, or it can release heat, because it's you are seeing chemiluminescence from there. It can release heat only when you have flames extinguished along the shear layers. Okay. Either sideways or downstream, when the flame is extinguished along the shear layers, only the fresh mixture can entrain through the shear layers and pass through the shear layers unburnt and go into the recirculation zone, and due to the favorable time scales there can react to produce this heat release, and which produces this chemiluminescence. Okay. So this is, then the question is this: is this what is happening before blow off, that is the flame is extinguishing along the shear layers? So then but of course chemiluminescence is a qualitative technique, it does not give you the full idea. So what we need to do is that we need to use these high speed high fidelity techniques like PIV PLIF to basically understand what is going on. Okay. Now before that we also get this this is a final blow off event. Okay. Do you see recirculation zone burn in the final blow off event also? Yes, it is indeed the case. You see that under normal circumstances here you do not see too much of reactions here, right, because you have had a flame there. But now as soon as the reactions become weak, you see the flame is there is no flame here, and essentially the product that goes in, it can go in through here, and by the time it enters it can burn inside the recirculation zone, and that can lead to essentially flame blow off. Okay. And this adds to the shape the direction of the flow from top bottom to top. So, you see the flame blow off is characterized, with which we observed for the first time, that the flame blow off is characterized by this event called recirculation zone burn. Okay. That is, under recirculation zone, under in normal circumstances contain only hot products, but just before blow off it emits this chemiluminescence, which tells us that the flame must have extinguished along the shear layers, and as a result of that the fresh mixtures can pass through the shear layers unburnt, and by the time it gets into the recirculation zone it still remains unburnt, and but now due to favorable time scales there, it is recirculating, it can burn and it can produce this emission, and it can also produce this chemiluminescence, which tells us that there is reaction going inside the recirculation zone. Okay. So, is it really the case? Does PIV also tells us this? And the second thing is that why does the flame extinguish along the shear layers? Approach, as blow off is approached, what causes the flame to extinguish along the shear layers? That is a question. So, for that we did PIV and PLEF simultaneously at two cases, one for stable flame which is far from blow off, and the other is for the unstable flame which is more near which is more close to blow off. Okay. So, what happens for the stable flame? You see that yes, this flame is there and you see wrinkles because you have Kelvin-Helmholtz vortices. Okay. These are this Kelvin-Helmholtz vortices, this is the positive vorticity, this is the negative vorticity, because they are in this way it is rolling like this, in this way it is rolling like this. And if we extract the flame edges, you see this very sharp flame boundary is formed. Okay. And if we extract this flame edges by this large gradients, maximum gradient of OH by mathematical by algorithms like Canny edge reduction, etc., we see that the flame edge essentially envelops this Kelvin-Helmholtz vortices. Okay. Kelvin-Helmholtz vortices are inside the flame edge. Now, what happens as blow off is approached? You see this large regions of flame holes are formed. Okay. Flame hole is formed, flame hole is formed. Okay. And more interestingly, you see that this flame edge is essentially overlapping this Kelvin-Helmholtz vortices. Okay. Of course, the flame is much more distorted shape, but it is overlapping this Kelvin-Helmholtz vortices. And of course, you see this large flame holes being formed and this large regions of extinction being formed, and once again invariably you see this flame edge now overlapping this Kelvin-Helmholtz vortices. Okay. Now, if you look at this, these are of course one images, you cannot comment on something to be a mechanism. When you just see one image, you have to get the statistics. So, if you get the statistics, you see that this is far from blow off, this is near blow off, red is for OH on the right hand axis, this blue is for velocity on the left hand axis. So, you see that this OH has a kind of a bimodal peak like this, you see, and this OH peak essentially corresponds to the maximum vorticity, this says that statistically also the maximum OH is located inside this shear layers. Okay. Now, as blow off is approached, you see this bimodal distribution in spatial distribution of OH is lost, and you get a single like a central distribution. Okay. So, this says that you cannot statistically you cannot find maximum OH along the shear layers. You can now statistically you find maximum OH inside the recirculation zone like this. Okay. So, you see that the vorticity structure has not changed, on average has not changed too much, okay, but the OH structure has changed, and there is no OH on average along the shear layers. So, that shows that there is no OH, which is a marker of the reactive which is essentially a reactive intermediate and a marker of the most important combustion chain most important elementary reaction, that is a chain branching reaction, H plus O2 going to OH plus O. Okay. So, that reaction is that thing is not happening along the shear layers anymore. So, the flame on statistically is settled inside the recirculation zone, and you do not have a flame along the shear layers. Okay. So, that means that the flame is extinguished along the shear layers or it has gone inside. So, you see this consistently here also, that at along all locations 10 millimeters, 20 millimeters, 30 millimeters for all these things. If you look at this, you have bimodal distribution of OH at equivalence ratio 0.9. Near blow off at 0.77, you see this unimodal distribution of OH, and this flame has the flame has extinguished along the shear layers. Same thing you can get from conditional PDFs also. Okay. So, Then the question is that what causes the flame to extinguish along the shear layers. For that we need to basically go back into the basics of premix flame extinction by heat loss and by stretch. Okay. And if you remember that if you have extinction along the if you have heat loss for a premix flame, okay, and this heat loss can be caused by a Lewis number greater than 1 premix flame when it is under positive stretch, you have this kind of a response. Of course, this is for a 1D flame, okay, it is a 1D analysis, but you saw that this was the F tilde is essentially the your normalized burning flux. So when the heat loss is at this point about this value E inverse, then you have a turning point in F which corresponds to extinction. Okay. So the heat loss at this state, this e to the minus 1 is sufficient to cause the flame extinction. You also discuss the concept of stretch, okay, that if you have stretch, also the question is that the point is that you have exactly the same analysis, same result as you have by heat loss, because what stretch causes for a Lewis number greater than 1, if this stretch kappa is greater than 0, then you have heat loss and you have this kind of an extinction behavior. Okay. And our flame is essentially a propane air flame at phi equal to 0.77 near blow off, and that has Lewis number greater than 1. Okay. Sorry. .77 near blow off, and that has a Lewis number greater than 1. So if it is undergoing stretch, it can, if positive stretch, it can exceed, it can undergo, it can be blown off, it can extinguish locally, and that can lead to blow off. Okay. So now we look into the PDFs of strain rate along the OH Piliff edge, which can be obtained by this formula. That is essentially this is a projection of it is a projection of the strain rates along the flame tangent. Okay. If you do that, okay, you find that and find the PDF, of course, because this is a turbulent flame, you cannot have one value of stretch along the entire flame surface. So you basically generate a probability distribution for a density function. Okay. So the PDF says that at equivalence ratio 0.9 you have this is the PDF. Okay. You have this as the PDF. At equivalence ratio 0.77 your stretch PDF is like this. Okay. That means as blow off is approached, is the stretch PDF or the flame stretch increases for most part of the flame. On the other hand, the extinction strain rate, that is the maximum strain rate laminar opposed premix flame can sustain, which is a measure of the strain holding capacity of a flame before it undergoes extinction, that reduces. So that reduces from this value from near about 2500 to less than 2000, whereas this actual strains increase. So this causes an opposing movement. On one hand, the strain level of the 0.77 flame is increasing, that is, it is undergoing more straining, but its strain carrying capacity or its strain holding capacity is reduced because its extinction strain rate is reduced. As a result, what will happen? The flame will extinguish, right. So its strain has exceeded, its actual strain has exceeded, but its limiting strain has that the threshold strain that it can accept, that is reduced, so it extinguishes. So essentially it is the shear layer flame extinction along the shear layers that allows this flame to be the shear layers to be free of the flame, and when the shear layers are free of the flame, the fresh mixture can entrain through the shear layers and it can go into the recirculation zone unburnt, and it can react inside the recirculation zone due to favorable time scale, and that is why we get high amount of chemiluminescence and large heat release from the recirculation zone just prior to blow off. So this is the thing. So the one question we did not answer is that why does this shifting happen? Why does the PDF shift into the right direction, that is, why does the flame get more strained as it approaches blow off? The reason can be understood from here. You see, at equivalence ratio 0.9 this flame was enveloping this Kelvin-Helmholtz vortices. So, the flame cone angle like this was large because its average flame speed is large, its turbulent flame speed is also large. But as the flame speed reduces, okay, to balance with the local normal velocity, the flame angle reduces, and you see the flame is much more columnar now. Okay. Now, as the flame from a conical flame becomes a more columnar flame, instead of overlapping this Kelvin-Helmholtz vortices, now it gets instead of so this was essentially enveloping the Kelvin-Helmholtz vortices. So, while the flame was a conical flame, the flame was enveloping the Kelvin-Helmholtz vortices, but as the equivalence ratio is reducing from a conical flame, the flame becomes a columnar flame, and so that because its flame speed has reduced, and to balance with the local flow field, for the cone angle reduces. It can be easily shown, you should show it actually, that how does the flame cone angle reduce and it becomes more columnar as the flame speed is reduced. But the fact of the matter is that as the flame cone angle reduces, that the flame becomes more columnar, instead of enveloping this Kelvin-Helmholtz vortices, the flame now essentially overlaps with this Kelvin-Helmholtz vortices, and these Kelvin-Helmholtz vortices can impart strong strain on the flame surface, and that essentially cause the PDF of this strain on the stretch rate on the flame surface to increase in the right hand side, to increase and to proceed towards the right hand side, and of course the extinction strain is reducing. So, now you see here at 0.9 only is very small, this percentage, this amount of the flame exceeded the extinction stretch rate. So, there is very small extinction, but now you see that whole of this part of the flame is now exceeded the extinction strain rate. So, as a result, of course, it causes the flame to extinguish, and thus the shear layer, essentially the flames extinguish along the shear layers, because that is what the maximum strain is, and now the fresh mixture can pass through the shear layers and can get into the recirculation zone and can react there due to favorable time scales. Okay. So, we see the stage 3 in blow off dynamics, and which also is characterized with this recirculation zone burn, which we clearly see that from the PLIF images also, that you see this maximum OH, the super equilibrium OH happening along the recirculation zones inside the recirculation zone, and this recirculation zone burn, that is the strong PLIF signal from the recirculation zone, cannot be obtained in a normal circumstances. So, this is the hallmark of this work, where we essentially formulated how the blow off essentially happens in the to cause the which connects the initial inception of this flame holes to the final blow off event. Okay. So, in the next so this was done in a small laboratory experiment. In the next class we will see that we will basically do these experiments in a real engine like configuration, and we will see if this in a different Reynolds number, higher Reynolds number, different geometry, whether this mechanism still holds or not. So, till then, goodbye.